Okay, start please by writing down what you remember of Snell's law. Now you have started the show again, and I hope this is what you wrote. We worked out the geometry of this. It makes a lot of sense. It's lovely, but we don't get to leave things like that because physicists, opticians don't like to work with the velocity of light in the mediums. Instead, they like to work with something called the index of refraction, this n. And the definition of the index of refraction, which you have to know, is that the velocity of light in a vacuum divided by the velocity of light in medium x is the index of refraction for medium x. And so if we take Snell's law, which made so much lovely geometric sense, and we replace the v's by this ratio where I put it over ni so I could have vx over here, then you can see that this reduces to this, and then people do a little bit of algebra, and if you look in a textbook for Snell's law, this is what you will see. And you will need to work with this formula in conjunction with these to do various problems that you will have light coming up to an interface between two media, and of course energy is going to be reflected at the same angle as the angle of incidence. Remember that you measure the angles to the normal, and you ought to also be able to tell me whether this is entering a faster or a slower medium here. But you would then, perhaps it is a problem where they told you the index of refraction, ask for the index, they told you the angle of incidence, ask for the angle of refraction, and then you would look here to see, oh, what is the index of refraction for the incident medium, which might be air, and what is the index of refraction for the refracting medium, which might be water. And of course, notice that all of these are bigger than 1 because all of the velocities are going to be less than the velocity in a vacuum. So you be sure that that always turns out the case. If you ever get the index of refraction smaller than 1, you know you've made a mistake. That this water having an index of refraction of 4/3 means the velocity of light in water is 3/4 as fast as it is in the vacuum of space. That diamond having a very large index of refraction, that means the light goes very slow. Goes at about 4/10 the speed that it does in the vacuum of space. So do the problem. Now I'm going to deal with a unique instance where light is going from a slower medium into a faster medium. And again, recall, to be faster means it has a smaller index of refraction. The larger the index of refraction, the slower the light goes. And of course, at that change of medium, there's going to be reflection and refraction, and we need a normal to talk about this. If it's going into a faster medium, how would it be bent? And I hope that your answer was that it would be bent away from the normal. And that bending away from the normal is why it is so important that we go from water into air. The phenomenon I'm about to share with you, does not happen if you're going from air into water. You have to be going from slower into faster, because you get this bending away from the normal. And so there is the possibility to bring the light in at such a large angle of incidence that the angle of refraction becomes 90. It shoots right along the interface between air and water. The light is bent so much upon entering the air that it doesn't enter the air. But if it didn't enter the air, how did it get bent? Refraction ceases to make sense. And we say that at this point, instead of some of the energy being reflected and some of it being refracted, all of it gets reflected, and you have what is called total internal reflection. That when you do problems, you will take Snell's law, but this angle we're going to be talking about here is called the critical angle, and this angle is going to be 90 degrees, and the sine of 90 is 1. And so you have a formula like this that you would use to solve for what the critical angle was, or given the critical angle, what the index of refraction is, or some such mathematical manipulation. And here you are. Do it. Okay, so here we have light entering a triangular chunk of glass. It's coming in sort of parallel, and upon entering that chunk of glass, it does not continue straight, but it gets bent closer to the normal. Here, I'll give you a sense of straight. It doesn't continue straight, gets bent closer to the normal, and then as it leaves the chunk of glass and goes back into the faster air, it does not continue straight, normal. It gets bent closer, further from the normal, because it's going into a faster medium. And if we were to bring in, not that, a whole bunch more, they would also be bent down towards this axis. And if we had another chunk of glass on the bottom, then we could bring the light down here at the bottom up, and we could bring the light together. We could converge the light. We could take the light which was spread over this large area and cause it to be over a smaller area. We could make the light more intense. And that is a cool thing to do. But I'm not satisfied. I don't want to just bring it together. I wanted to bring it all together at a point. And so I'm going to take the light that's coming in further out. I want to bend it in more. And the light that's coming further in, and I want to bend it in less, so I can bring all the light together. And the way that I do that is to reshape the glass so that it bends the light a lot out at the edge, and bends the light a little bit less here, and even less here. And as you get towards the center, I want to almost have the sides be parallel so that it doesn't bend the light hardly at all. And I get a chunk of glass like this, which will then take that light which is coming in and bend it a lot out at the edge, and bend it less as you come in towards the center, so that all the light comes together at a point which is called the focus. That is the Latin word for the hearth. It may not be the one you learned, but it is. And that was the gathering place in the home, and this is where the light is gathered together. The Greeks, making these little shapes, which in 3 dimensions are going to be thin out at the edge and fat in the middle, said that looks just like the lentils that we like to eat, and so they called them little lentil beans, and the Greek word for lentil is lens. And that's what we call them. And if you go to Greece, you can have some lens soup. Okay, so here is a lens, and the light is being bent in, and we, instead of having it bend as it changes medium at these 2 sides, we are going to do what's called a thin lens approximation, and we are going to say that, where are you? We are going to say that all the bending happens in the middle. So we will only bend it here in the middle. And the lens has an axis of symmetry, and the place where the a ray coming in parallel to the axis is bent so that it crosses the axis is called the focus. And unlike a mirror, a lens has two foci that are going to be equidistant on either side of this point at the center of the lens where it crosses the axis, which is called the vertex. And just like with a mirror, we will measure all distances from that vertex in the center of the lens. And so, just like with mirrors, we're going to have rays which come in parallel and are bent through the focus. Notice here's another focus over here, but that would be a reflection for it to go back through the focus. This is a lens. It refracts the light. The light goes through and gets bent through the focus. And a ray which goes through the focus is bent parallel. And where those two come together, that would be where the image is located. Just like with mirrors, there is the option of yet a third, instead of through the center of curvature, reflected back through the center of curvature, this time it's going to be through the vertex, that place of little bending. It gets unbent. And again, as with mirrors, you are advised to avoid drawing a third if you can avoid it, because it will create confusion if it doesn't come out exactly right. Notice your image. Okay, now I would like you to do that for this one. Don't look back at the image. And just like with a mirror, things get very interesting when you are inside the focal length. You may remember how we dealt with that with a mirror, in which case you try to stay a step ahead of me. And you can fill in your worksheet at the same time, but please don't just copy. Try to stay ahead of me. So what are we going to do? Well, we have the same rules that we used here. Parallel through the focus, parallel. So a ray which comes in parallel, and I would go right to the center of the lens. It gets reflected through the focus, and a ray which goes through the focus, grazes the tip, and hits up here. That is, it would not, if you went from the object through the focus, you would never hit the lens. But if we go through the focus and a ray leaving the tip of the lens, which is going in the direction from the focus, gets bent parallel, put these arrowheads on. This is what your eye, you look through the lens to see this object, and your eye sees light which is diverging. It does not come together. Your brain, however, being of the opinion that light travels in straight lines, extends these rays backwards and finds that there is an object at this point, and it ought to have its base on the axis. Okay, notice again, virtual images, those not formed by the actual intersection of light, are going to be right side up. And for converging, when you get a virtual image, it's going to be enlarged. Now on to diverging. And this is going to be a different situation. A ray which comes in parallel is not going to continue in a straight line, that we are entering a slower medium, and so instead of continuing straight, it will be bent closer to the normal, and then as it leaves, instead of going straight, it will be bent away from the normal. Here, let me get you a normal. It will be bent away from the normal, that instead of going straight, it gets bent away from the normal, and what you have is, come on, I don't need that. is light which has been diverged. I'm trying to go fast. Again, we are going to do a thin lens approximation, and we are going to say that all the bending happens at the center, and that bending that happens at the center is going to again be parallel through the focus, but we wouldn't go through this focus. That would be converging the light. We need to diverge the light. And a ray which is headed for the focus is going to be bent in the center of the lens so that it goes parallel. Again, put the arrowheads on. This light is diverging, but your brain, thinking that light travels in a straight line, extends these two lines backwards, and it sees an image. Just like for a mirror, with a diverging, you only get virtual images, and they are all diminished. Again, there is the possibility, should you wish to entertain it, of doing a third ray, maybe an easier ray. Maybe you ought to left out one of these, that goes from the vertex through at the vertex and so is unbent. And again, you get confusion if you draw the third. I would stay away from it. Okay, will you please try to mimic what I just did for this diagram. Now to the mathematical treatment, just like for mirrors, you have hi-ho, di-do, and soft magnification we go, and if I do, I die. And just like for mirrors, the negatives are very important here. They indicate that things are in the wrong place. I would ignore the negatives when you were dealing with the magnification. Wrong place. Well, to get an image on the same side of the lens as the object is the wrong place now. So that's what a negative distance means, that it's supposed to be making an image over on the other side of the lens. So that would be a positive distance if you get images on the other side of the lens, and a negative distance if it's on the same side, and if something has negative focal length, as this one does, then what kind of lens is it? Indeed. Off you go. And another problem. And before we talk about eyes, I need to establish that thin lenses bend the light a little and fat lenses bend the light a lot. Here in this example, for these chosen indices of refraction, I have the light coming in, and because it's a thin lens, this angle is only like 10 degrees, and you get an angle of refraction that's about half as big. And again here it's about half as big, but because the angle of incidence is bigger, the light has been bent by about 15 degrees here, where here was only bent by about 5 degrees. Factoid. Fat lenses bend the light a lot, thin lenses bend the light a little. And that is going to be true for this lens in your eye. But the major bending does not happen at this lens. It happens at where there's the biggest change of indices of refraction, the biggest change of velocity, and that is where you go from air into eye stuff. And that point is called the cornea. And sometimes we do surgery and reshape the cornea. It's called a keratotomy, and that changes how we bend the light to correct for vision problems. Back behind the cornea is an opaque curtain that stops the light. There's a hole in the curtain, so involuntarily there is control over how much light goes into the interior of the eye. The curtain is called an iris, that's the colored part of your eye, and the hole is called the pupil. And the pupil gets bigger when there is less light and smaller when there's more light, but it also gets bigger when there is affection, and it gets smaller when there is animosity. And Aristotle coined this name for that hole because he liked his students to have big holes. He liked them to feel affection and appreciation for what he was doing. Following the iris and pupil, you have this lens, which you can change the shape of. When you flex the muscles around it, that causes it to relax and get fat. When you relax the muscles around it, that causes it to get fat. When you flex the muscles, that pulls it thin. And remember that fat lenses bend the light a lot and thin lenses bend the light less. Here at the back of the eye is this retina that you are trying to bring the light into focus on, and the fact that you are trying to form real images there means that they must be inverted images. And we will tease around with the fact that everything you see with your eye is in fact upside down to what you are seeing. Or not. So, eye problems. If you are looking at something close up, you need to bend the light a lot. You need a plump lens. But when you look at something far away, you need to bend the light less. You need a thin lens. But if your eye will not go thin, if it stays too plump, then you will bend the light too much and you do not get a good image. These people can see things close, but they cannot see things far away. They are called nearsighted, and the correction for that is a diverging lens, which bends the light out, and then this over-bending lens bends it back in again. This is typically the problem of young people whose body parts are very flexible and resilient. It is called myopia in Latin instead of nearsighted. This is the problem that older people have, lenses that do not plump up, that I look at things far away, and there you need the lens to be thin, and our lenses are nice and thin, and they bring the light together. But when we look at things close up, we try to read, we need the lens to plump up. And so we flex. Yeah, I got that backwards. You flex the muscles to try to allow the lens to plump up, and it doesn't plump anymore when you get old. And so we need reading glasses. We are able to see far away. We are farsighted. We need a converging lens to help us because this thin lens will not bend the light enough. Latin name is hyperopia. Thank you.